Alright, so we are proving things about sets of content 0 and their boundaries. Um, and actually, not just, well, part A is about sets of we're proving things about the boundaries of sets and how the boundaries will relate to um, their measures. So, part A, we're proving that the boundary of a set of content 0 has content 0, but for B, the boundary of a set of measure 0 does not need to have measure 0. So this is just one example of a way in which measure theory is sort of weird. But it gets a lot worse than that. Or better, depending on your viewpoint. But let's start with A. So, suppose C has... Here, let's just try that out. Suppose C has content 0. So the idea here... Well, no. I'll get to that later. Given epsilon greater than 0, let u1 through u... so here, we don't have any dimension here, so I'll call it un. Be a finite cover. Well, there's finitely many of them, so if I can just say cover, and you'll know it's a finite cover of C with the sum of the volumes being less than epsilon for some given... Oh, well, we said that already. Alright, so let U be the union of all the UIs. Okay, so what we could do now... So then U is closed, because we know that if you take the union of finitely many closed sets, then you get a closed set, because that's how topology works. Okay, wait, is that necessary? Yes, it is. Okay. So it's necessary for both proofs. And the reason I say both proofs is because there's a really easy proof that you can do if you know a little more topology, and then an also not difficult but slightly more sentences proof that you have to do if you just know the stuff from this textbook. Okay, so the boundary of a set, as defined in this textbook, consists of all points such that any neighborhood of that point intersects both the set and the complement of the set. Now, an equivalent definition is that so we have something called the closure of a set. And the closure of a set is the intersection of all closed sets containing that set. And the closure can also be defined as the smallest closed set containing the given set. And it turns out that the closure consists of both, or the closure can be written as the union of the boundary of a set and the interior of the set, where the interior of a set is defined as the largest open set contained in a set, or the union of all open sets contained in a set. And so if you know this, you also can, well, okay, so the closure of a set is closed, and it always contains the set that you're given. So then what you can say is you can say, okay, well, so U is closed, and it contains the set C. Now consider the closure of C. The closure of C is a closed set, which can... the closure of C is the intersection of all closed sets containing C. So in particular, that means that the closure of C must be contained in U, since U is a closed set which contains C. And so what that allows you to prove then is that, so the set U contains the closure of C, and the boundary of C is a subset of the closure of C. So you know that U contains the closure of C, but that means precisely that U1 through UN covers the boundary of C. So you have a finite cover of the boundary of C, And we already know that the sum of the volumes is less than epsilon, and so you have satisfied the condition necessary to prove that the boundary of C is a set of content 0. Okay, so that's how you would do it if you knew things about boundaries and how it's defined in terms of closed sets and how it's related to the boundary. Yeah, closures, boundaries. I may have mixed up the words closure and boundary a couple times in there. Maybe I need more coffee. Alright, so now going back to what we're doing here. So we know U is closed. If X is not in U, then there is a neighborhood, an open neighborhood V of X, which does not intersect U. And we know that this is true because U is closed. So if it were the case that every neighborhood of the point X intersected U, then X would be a limit point of U. And closed sets contain their limit points. And so it would be true that X would be contained in U. But we know that that's not true because we assume that X is not in U. I wonder if all of that vocabulary I just used is stuff that we know in this textbook. It's a little vague. It's a little tough doing these exercises, knowing that the author has introduced only a subset of sort of basic point set topology. So I'm sorry if there's anything I mentioned that we don't know. Yeah, I'm pretty sure all that stuff can at least be phrased in some way using, because everything in this textbook I think is phrased in terms of neighborhoods. Okay, so if X is not in U, there's a neighborhood, blah, blah, blah. So that means that X cannot be in the boundary. Wait. Okay, we're not quite there yet. So it does not intersect U. Now C is a subset of U. Since C is a subset of U, V does not intersect C either, because if it did intersect C, then that point would be a point in both C and V, but C is a subset of U, so it would be a point in both U and C, which we know can't happen. So since C is in U, V does not intersect C, so thus X is not in the boundary of C, because for X to be in the boundary of C, any neighborhood, if X were in the boundary of C, then any neighborhood of X would contain both points in C and not in C. However, we have shown that there is a neighborhood which does not contain any points in C. Okay, so X is not in the boundary of C. So if X is not in U, then X is not in the boundary of C. So this means, so if X is not in U, then X is not in the boundary of C. Contrapositively, if X is not in the boundary of C, i.e. if X is in the boundary of C, then X is not in U, so X is in U. Which is precisely to say that the boundary of C is contained in U. So then U1 through UN, because it covers U, also covers the boundary of C. Wait, no. Well, no. U1 through UN is precisely... Their union is precisely U. So U1 through UN covers the boundary of C and the sum of the volumes. UI is less than epsilon because we already know that. Hence, the boundary of C has content 0. Okay, so now we need to give an example of a bounded set C of measure 0 such that the boundary of C does not have measure 0. Okay. So now what we're going to do is we're going to look at, so we know that C, so let's see here. We know that Q has measure 0, the rational numbers have measure 0, and then I'm forgetting what theorem 3-4 is. So I'm actually going to pull this up real quick. Is it literally just that, oh, a union of, oh, okay, it's gone. And it's gone. And now it's back. And where are we? Why are we at the end of the thing? Okay, so I'm pretty sure we proved in the textbook that the rational numbers have measure 0. And if you have a subset of measure 0 that has measure 0, okay, so, wait, so let me remember what we need here. We need a bounded set of measure 0 whose boundary does not have measure 0. So let A be, we're going to take the rational numbers and intersect with the interval from 0 to 1. Okay. Q has measure 0, so A does 2. Because Q has measure 0 because I'm pretty sure we talked about how you can cover each element of Q by an interval of length epsilon times 2 to the, you can label the elements of Q by like 1, 2, 3, etc. And so for the ith element of Q, you cover it by an interval of length 2 epsilon times 2 to the minus I, and then you end up with a cover of Q whose total volume is epsilon, and epsilon is arbitrary, and so Q has measure 0. Okay, and A is a subset of Q because it's just Q intersected, the rationals intersected with this finite interval. So any cover of Q covers A, and so A has measure 0 as well. Okay, so now the boundary of A is going to be what? It's going to be precisely this set, the closed interval from 0 to 1, because for all x in this interval from 0 to 1, any neighborhood of x contains rationals and irrationals in 0, 1. And you can prove this in more rigor than I have done here if you really want to. Like, for example, what you could do is the worst case scenario is that x is either precisely 0 or precisely 1. But then, let's say x is 0, choose any neighborhood of x. So that will be an interval that goes from like some negative number. Well, it's a rectangle. Worst case scenario, it goes from 0 to some positive number y. Y will be greater than 0. And so you have an entire, this neighborhood contains the interval 0 to y. And that interval will contain both rationals and irrationals in the interval from 0 to 1. And so you're good. Similar thing with if you choose x equal to 1, then if you choose any x in the interior of 0 to 1, then, i.e. any element of the closed interval from 0 to 1 other than 0 and 1, then again you just take some neighborhood and that's going to be an interval, and so it's going to have rationals and irrationals, and that's still true if you restrict your focus to only the part of the interval that overlaps with 0 to 1. I guess technically, I wonder, maybe this is technically open parentheses here, because if you take no, it's the open covers that we talk about can be either open, or the covers that we talk about in defining measure 0 and content 0 can be open or closed. However, the reason they can be open or closed is that it doesn't affect the volume. However, when we're talking about the boundary, we do need open intervals. So if you have an open interval of 0 or 1, you are going to land a little bit in that interval from 0 to 1. Okay. So yeah, any x in 0, 1, any neighborhood of x contains rationals and irrationals to 0 and 1, and so that's what it means to be in the boundary. So of course, the volume. Okay, so we're proving that so we also know that the measure, I'll just say, because I'm running out of space here, the measure of the interval from 0 to 1, well, it is 1, but actually proving what the measure is, it turns out, is a little difficult. But we know for sure that it's greater than 0 because that's a theorem that we have. Or does the theorem actually give us that the measure of the interval is precisely the difference of the endpoints? It should be, because that's what it is, but I don't know if it goes ahead and proves it. But in any case, it certainly proves that the measure is positive. So what we do is we have a set of measure 0. Wait, what are we looking for here? No, a set of measure 0 whose boundary does not have measure 0. So we have a set, and the set has measure 0, but the boundary of the set does not have measure 0. In fact, it has measure 1, but in particular, it's not measure 0. Now, the only thing that I'm thinking here is, does that theorem about the measure of an interval, I think that might actually talk about the content. But, so basically, what that theorem will prove is that if you have a finite cover of the interval from 0 to 1, then that finite cover, the sum of the volumes will be greater than or equal to 1. So in particular, if you had an infinite cover, then the same would have to hold true. Although the argument might be a little trickier. Let me just make sure that we got this. Alright, so I got it. So then use theorem 3-6. Because what that says is that a compact set that has measure 0 must have content 0. So, if we look at this closed interval from 0 to 1, if it's compact, and if it did have measure 0, then it would have content 0. However, we know from the theorem in the textbook that it does not have content 0. Therefore, it cannot have measure 0. And so, this closed interval from 0 to 1 certainly does not have measure 0. And so we indeed have an example A of a set which has measure 0, but whose boundary does not have measure 0. And so you may have noticed me at the end there, like I got a little confused on what we were doing, and then I went in the textbook and looked at the things that are proven in the textbook, and it might seem a little weird because like we sort of have like just a strange combination of theorems and results in this section of the textbook, where you have things about like unions of sets of measure 0 have measure 0, I think is the theorem. Then you have intervals have content 0, and then you have this sort of random looking argument that's like, if you have a compact set that has measure 0, then it has content 0. So you might be like, why are these the theorems that are included just this sort of random collection? So basically what it is I'm pretty sure that these are the things that are going to be needed later on in this section. And the author just wanted to include only the things that were absolutely necessary. And the reason that we did that is that this is all sort of coming from measure theory, and measure theory is really weird. So if you're just introducing a few facts from measure theory to use later on, you don't want to grab too many things, because a lot of these things are really weird, and you're just trying to do like the bare minimum. And so that's why if any of these theorems seem sort of like, okay, where did that come from? Why are we like here we're talking about sets of measure 0 compared to content 0. Like, why do we need that? Like, should there be an easier way to prove that that the interval from 0 to 1 has measure, or shouldn't there be an easier way to prove that the interval from 0 to 1 does not have measure 0? And in fact, can't we prove that it has measure equal to 1? And it turns out no, because measure theory is really weird. And so that's why we're sort of not doing any of these things that would sort of seem like things that we could do easily. It turns out they're not easy to do. And if you actually want to do them, then you can probably just like go read Folland or some other measure theory textbook. It's really neat, and it's really necessary for proving integration in what I think is like a more general way. Well, it is absolutely a more general way, but it's weird and it takes work, and it's not necessary for this textbook. So we don't do it. We only grab the things that we need, and it may look weird, but if we grabbed more, it would look even weirder. So yeah, but in any case, so this also shows you how like if you have sets of content 0, their boundary is also going to have content 0. So in that sense, sets of content 0 aren't super weird. Whereas you can have sets of measure 0 whose boundary has measure not equal to 0. And in fact, if you were to, instead of intersecting the rationals with 0, 1, you could intersect with 0, comma, some number y, and then you could get a set with measure 0 whose boundary has measure y. So yeah, so sets of measure 0 can be a little weirder. Um, so that's part of the point of this exercise. And yeah, we've done the exercise, and so there's nothing more to do.